live virtual classes organized by the Board of Studies Academic, ICAI, in course of our discussion on quantitative aptitude paper 3. Today we are starting with a very interesting chapter, that is chapter 15 on probability, which we will be discussing from all detailed angles along with solution to number of questions on this particular chapter. So good afternoon, sir. I see Dr. Ravi sir is also with us, requesting, sir, if you can please give your introductory comments and guidance to the students.
Thank you so much, sir. Welcome to the live virtual classes. You are most welcome here, sir, for delivering the sections on probability. Today's topic is very interesting, and only thing is they have to focus attention on their probability on concentration has to shift 100% on towards the otherwise the concentration is to be increased more. Once you understand this concept, it's a very lovely and interesting. Once you understand the puzzle also be this is quite interesting, and you can answer good number of questions also be. And moreover, this is a chapter having the good number of questions are also coming in the examination point of view also. 4 to 6 questions are expecting from this chapter. Don't forget this, and 6 questions of maximum questions we may expect from this chapter also be as per the weightage is concerned. Actually, you all know probability is used in accounting, finance, and to understand the likelihood of the occurrence of or non-occurrence of a variable also be. It helps to develop the financial forecasting, in which we need to develop expertise in the stage of the advanced stage of the risk management, or the course, and the probabilities are very much used at this. Actually, the expected rate of return, actually what would be the in the generally returns, when we know the probabilities of the things, and the expected probabilities are also be, expected returns are also some that, and what is the variance are also be, and we can find out from this actually. And we have the definition random what is the various definitions related to the probability, just that has to be understand before understanding the concepts of the probability also. What is experiment? Means a random experiment here, mutually exclusive or like incompatible event, and exhaustive events, equally likely events, or mutually symmetric events, or equiprobable events. And about the definition of the probability also be, that is the classical definition of the probability, as well as the uh, axiomatic approach also be, that is about the statistical definition of the probability also, and various operations of the calculation. This is derived from once you understand the set theory also, from the union and intersection concepts. Based on that, we are using here addition theorem, as well as the multiplication theorem. Means here we can say that in a different angle, that is intersection, that is the probability of A given B by our Bayes theorem also be approached also here. And come to the important aspects, and the probability lies between 0 and to 1 also. The probability of non-occurrence of event is 0, and the probability of maximum occurrence of an event is chance is 1 also. This is just a basic background I had explained. So now Sari is with us, and over to Arjit sir, and welcome to you once again, sir, for making us understand the subject also very interesting, and understand none other than better than you can deliver this topic also be. You have been delivered so many times. I had seen you, I had watched you also these sections from the from 2020 onwards also. I had seen you actually when it was during the COVID times also be. You have delivered in the same platform, online live sections also with this background. I welcome once again, sir. Over to you for
You,
delivering
you,
this interesting topic.
yes.
Probability is very interesting topic. Now, students are ready to listen actually.
Thank you, sir. A very good afternoon, sir. Once again, thanks to sir. Good afternoon to all the students. And we are very thankful to sir for giving us, first of all, the overall understanding of this important chapter on probability. Sir has given us another, I will say, very useful information, and that is the number of marks. So you can see that the number of questions according to the weightage, as sir mentioned, 4 to 6 questions. That means if you understand the basic principles and the theorems, ultimately you will be able to score very well in this chapter. And as per our last chapters, we covered measures of central tendency and dispersion, standard deviation, variance. Here you will see that we will use the direct application of dispersion, standard deviation when we go and discuss about the remaining part of the chapter, especially towards the end when we come to the expectation and all. You will see we will use our knowledge of variance, standard deviation. The discussion for chapter 15 will be like this. First, we will understand what is meant by a random experiment. And then we will see that every random experiment has certain results, or you can call it outcome. Now, for example, we say that I'm studying for my CA foundation exam. So I may either pass if I put in my efforts, if I listen with full concentration to the LVC, if I practice under exam conditions, if I follow the ICAI study material and consistently prepare myself, yes, I will pass. That means the probability of my passing the exam will be 100% if I follow all these important tips and if I put in my efforts and sincerity. So examination, passing in an examination is sometimes seen as, we always say that, is it likely that I will pass this time? Is it probable that I will pass this time? Is it probable that I will be successful in the examination? So you see, every experiment, random experiment, when you flip a coin, when you toss a coin, so it is an experiment and it will have an outcome or a result, and this is known as event. Then we will see how probability is linked. Like if I just asked you that, yes, when you just toss a coin has two faces, two sides, head and tail. So you know that if I ask you that what is the chance or what is the likelihood or the probability that you will get a head. So then you will think that using common sense, so probability is such an easy topic as well as interesting that it is based on common sense. You will think that, okay, there are two possibilities. Either it's a head or it's a tail. And the question is, what is the chance that you will get a head? So you will simply say 50%. That is half. Why? Because there are two possibilities. That means it can be either a head or a tail. So two outcomes, two types of result. Either you have a head or you get a tail. There is nothing in between, right? So this is the basic concept of probability. And you can see this is like an experiment followed by an event. Similarly, when you are, say, for example, you are playing, say, for example, you are flipping, you are selecting a card from a shack, from a group of playing cards. You are just selecting a card. So yes, that is also a random experiment. So whether you get an ace or any other type of card, that depends on probability. And therefore, there are a number of practical examples. Then we will look at the formula, the concepts and the formula, followed by some theorems on probability. So please continuously listen and pay attention with full concentration. Only then we shall be able to successfully handle and solve some very interesting problems, which we will be doing in the next 2 hours. Please note that the probability theory and the principle, they have a lot of practical applications, as sir was mentioning, even in risk management, in the domain of financial management, there is a continuous application of probability. From probability, we will cover the understanding of expectation. We will learn what is meant by mathematical expectation, and then a brief discussion on the variables, that is discrete and continuous variables. And we have a very limited part of probability distribution in this chapter 15. In fact, we have a detailed chapter on probability distribution. That is the next chapter, chapter 16. But today we will have a brief understanding of what is probability distribution, because this is also covered under chapter 15. Finally, we will look at exercise 15. There are three sets of questions, A, B, and C. We will try and solve as many questions as possible. Finally, we will look at the type of problems which are there in the MTP and the RTP, and we will solve each of many of them using step-by-step approach, so that you can understand the reasoning, the logic, and the process by which we are going to arrive at the solution. Of course, probability has different theories, including we will have a separate formula for conditional probability, which we will see in due course. So the objective, why is this chapter included in your CA Foundation? As I was mentioning, this concept of probability, I was also narrating to you in the last session we had on chapter 14, where we had in-depth discussion on measures of central tendency and dispersion. I also reminded you to please keep in mind that dispersion, central tendency, not only a scoring part of our curriculum, but also has a lot of practical applications. Similarly, whenever we talk about probability, it deals with the likelihood, the chance that if I toss a coin, what will be the probability of a head? If I toss a coin 5 times, what will be the probability of getting at least 2 heads? If I am, say, sometimes, we are flipping, or we are just, say, a shuffling from a shuffle of cards, we are selecting a particular card. So what is the probability that a card is of a particular nature? Similarly, when we talk about likelihood of occurrence, it has a lot of applications in auditing, in finance, in risk management. Plus, based on your understanding of probability, even financial forecasting, which is very extensively handled by chartered accountants, you will be able to have a detailed knowledge of that as well, deep inside. In probability, I think the best application in banking. Now, bank is providing credit. Whenever they give a loan, they sanction a loan, a long-term loan, or a working capital loan, or a retail loan, a car loan, or a housing loan. They always think of that there's a chance that the borrower may not repay. So believe me, they will always find out the probability of default. So I take a loan, but I may become bankrupt later, or I may simply vanish from the country, or I may cheat the bank. So they will look at the probability of default. So for every credit decision, this is a standard practice. Then in risk management, we have something called value at risk, which is nothing but something called expected loss. And there we use the value which is involved and the probability of a default. So please see the successful practical application of probability. Even in the audit domain, there is always a chance of wrong accounting, wrong statement in financial statement, wrong reporting in financial statements. So the chance of misstatement in financial statements is included in audit, and we use the principle of probability. Similarly, in one of the earlier sessions, we were talking about Six Sigma, which is a quality control, a process management, performance management, quality management tool. And there, Six Sigma is used, and the probability of defectives, even for every manufacturing organization, entity, they will always try to find out what is the probability of a defective item which is produced. What is the probability of a service in a hotel? What is the probability that the service is delayed by 1 hour? Maybe you have ordered lunch or dinner and there's a delay. That means a substandard quality of service, or maybe the quality of service has fallen. So probability of defectives, whether in the manufacturing or in the service industry, is very important. Lastly, risk management. There can always be a probability of a failure of any operation, failure of an equipment. Even you think of aviation, there is always a probability of an air crash. But the probability is very less, no doubt. But airline operators, they will always try to find out the probability of an equipment of an aircraft going wrong in the sky when the aircraft is in flight, or when the aircraft is say taking off from the runway. You must have seen a lot of accidents taking place, but still the probability of failure, it can happen in any industry. This is mapped, this is quantified using the formula, using the principles we are going to learn over the next few hours. So the introduction to probability means chance. Sometimes in the exam, in the problems you might face, you might see a particular term which is called odds in favor, odds against. So probability is today, as we saw, a full-fledged subject. It is a very important part of statistics. Who developed probability? Yes, just for your reference, Simon de Laplace of France, the celebrated statistician R.A. Fisher of England, even the well-known mathematician Kolmogorov from Russia, they were instrumental in developing this scientific approach to probability. And as Sir was mentioning, that the value of chance or probability ranges between 0 and 1. So if there is a certainty that yes, I will win a particular match, if there is 100% certainty that I will pass an exam, if there is 100% complete, understanding, confidence that yes, I'm going to win a particular prize, then we say that it is a certain event. That means probability is 1, integer 1. On the other hand, if it is an impossible event, something which cannot happen, impossible event, it will have a 0 probability. So therefore, even if you think of the IMD, the Indian Meteorological Department, when you look at your apps, that what will be the weather in my city in the next 24 hours, or maybe in the next 1 week. So you will see the chance, you must have seen 30% chance, 20% chance of rain, maybe 50% chance of a sunny day. So even when we think of weather forecasting, or when we use apps related to the climate and the weather conditions, even when you are using navigation apps, they use probability. So they will tell you that this is the shortest route. So they have done all possible mapping of the routes, and they have calculated the probability of reaching the destination using different routes, and that route which gives them the highest probability of reaching your destination in the shortest possible time. This, the navigation software will show you as the most advantageous route. So you see probability behind every calculation. So the probability is a mathematical measure. It ranges between 0 and 1. That means probability can never exceed 1. Probability can never be negative. So the minimum is 0, the maximum value is 1. And very briefly, if you talk about it from a very introductory, a basic idea is probability means it's a ratio of fraction events divided by the number of outcomes. So when I am tossing a particular coin, there are 2 outcomes possible, either head or tail. I am thinking that what is the probability that I'll get a head? Head means I'm talking about 1 event. So therefore, the ratio or the probability of getting a head is 1 divided by 2, right? So it's half. So this is what we say is the basic introduction to probability. Now looking at the ICAI study material, kindly see on this slide, the next point to understand is random experiment. What is a random experiment? Well, random experiment means it is an experiment where the results depends on chance. Now, say for example, if you might be playing games of dice, right? So you have a die with 6 faces, right? From 1 to 6. So when you are, say, rolling a dice, there can be how many outcomes? There can be 6 outcomes. Either 1 will appear on the top, or 2 or 3. In this way, up to 6. So there could be 6 possible outcomes. If I ask you, my dear students, that what is the probability of rolling, if you roll a dice, a single die, you're rolling a single die, and what is the probability that you will get a number which is more than 4. Okay, so you are rolling a dice. What is the probability that you will get a number on the top which is more than 4? 1, 2, 3, 4, more than 4. So here you will think that, okay, the denominator of the probability formula is number of outcomes. So when I roll a dice, I will get 6 outcomes. So my denominator is 6. And now in the numerator, the question is that when I roll a dice, what is the probability of getting a number which is more than 4? More than 4 means there can be only 2 options. Either you get 5 or you get 6, because the maximum number on a dice is 6. You cannot get more than 6. And the question says that the number which will appear should be more than 4. That means either 5 or 6. So now you will think that, okay, number of favorable events which favor the question says more than 4. So to favor this question, to look at the favorable side, only 2 results or only 2 events or only 2 outcomes can be there, and that is 5 and 6. So now the fraction becomes the probability of getting a score more than 4 when you roll a dice becomes 2 by 6, because there are 2 possible events which will be favorable to you, and total number of possible events or outcomes is 6. So please see what the ICAI study material now says. I was just discussing the introduction to probability, the applications, the science, the principle. Now let us look at the formal definition of probability as given in the ICAI study material. And before that, we see random experiment. Please see, it clearly says that the experiment is defined to be random. We always say select a random number. Okay, you select a random book from the library. So this is random, means the results of the experiment depends on chance, number 1. And so the ICAI study material has cited the example of coin tossing. And see the logic, please. It clearly says that before you toss the coin in advance, it is impossible to say whether a head or a tail would turn up when you toss the coin once. So tossing of a coin is simply a random experiment because it is not possible for you to say with certainty that I will get head or I will get a tail when you toss a coin once. Similarly, the second example cited on this slide from this study material says that rolling a dice, or you might roll 3 or 4, multiple number of dice, or if you draw items, if you select items from a box has say 10 items, out of which say 4 are defective and 6 are good items. 4 are defective items. Total 10 items. Now you are allowed to select one object from the box. You know that the box has 10 objects. 4 are defective, 6 are good pieces. So now if the question comes to you that what is the probability that the object which you bring out from the box is of good quality, that means it is not a defective. So what will you say? Your reasoning will be like this, that the number of outcomes, there are 10 objects, so I can select an object in 10 possible ways. So the possible outcome is 10, and it is given that there are 6 objects which are good, 4 objects which are bad. And the question asks you, what is the probability that the object which you have selected from the box is of good quality, is good, it's not faulty, it's not defective. So how many events will go in your favor? There are 6 good items. So if you select any of the 6, you will be able to meet the requirement of the question. That means you can draw an object from the box in 6 ways. And here 6 ways means, if the question is that in how many ways can you draw or can you select a good item from the box, it will have 6 ways, because there are 6 objects in the box. So therefore the probability of drawing a good object from a box of 10 items where 6 are good and 4 are bad is given by how much? 6 by 10. So you can see even for selection of defective, non-defective items, drawing cards from say a pack of 52 cards, these are all examples of random experiment. So I hope you are able to understand that what is the concept of random experiment? Random experiment means that it will have the outcome is based on chance, and there is no way to predict with certainty that this will happen. So it is always a game of chance, you can call it. Now, for every random experiment, there will be certain results. These results, you can call it outcome, but technically, in the language of statistics, we call it event. So when you toss a coin, how many events can it result in? Well, it can have 2 events, either a head or a tail. When you roll a dice has 6 faces. So what are the possible number of events? Well, it will have 6 events. It can result in 6 type of outcomes or events. So you can see when a coin is tossed, it will have 2 outcomes. And therefore, we can say, what is event? Event means the result or the outcome from a random experiment. I hope it is clear. Random experiment is any experiment whose outcomes depend on chance. That means there is no way to predict with certainty that this is going to happen. And number 2 is every random experiment will have a result, it will have an outcome, and the result or the outcome is denoted by the term event. So event or outcomes or results, you can call it, they mean the same, but the technical term we will refer to is event. Now, the event could be simple, or it could be elementary, as we call it, or it could be composite or compound. Now, what is a simple event? Please see the example given and please focus your concentration, because these are the technical foundation of probability, after which we will move into the solution part. We will take a number of examples. An event will be a simple event if it cannot be decomposed into further events. So a tossing of a coin once, it gives you 2 simple events, either a head or a tail. But an example of a composite event can be bifurcated, can be decomposed, or can be broken down into 2 or more events. For example, getting a head. Say you are tossing a coin twice, as given on the slide, the example. You are tossing a coin twice. Getting a head when a coin is tossed twice is a composite event. Why? Because you can break it down into multiple events. The requirement given in this sentence is getting one head, getting a head. That means when you are tossing the coin twice, 2 times, either you get, when you toss it first, you get a head, and when you toss it again, you get a tail. So H and T, head and tail. This could be a particular sequence, or it could be the opposite. When you toss the coin once, you first get a tail, and then you again toss it. This time you get a head. So in the second, when you're tossing it for the second time, you get a head. So this is first tail and then head, T and H. So therefore you see this scenario, this situation gives us a composite event, because we can break it down into 2 simple events, 2 elementary events, and this is denoted by HT and TH. Now we come to mutually exclusive. Sir was requesting all the students, and he was mentioning mutually exclusive, equally likely. So these are the basic building blocks of probability, and we should be clear about these concepts. Mutually exclusive, 2 events or a set of events, it could be 1, 2, 3, multiple events, multiple outcomes, will be termed as mutually exclusive if not more than one of them can occur simultaneously. That means if one of the event happens, the other event cannot happen. So when a coin is tossed, you have only two possible events. Either it's a head or a tail. There can be no third scenario. Either a head or a tail. And now, will coin tossing be an example of a mutually exclusive event? Yes, definitely, because when head appears, if head appears, when you toss a coin, that means appearance of head means tail cannot appear. Head means you're getting a head. So tail, you cannot get a tail in the same throw of the coin. So these are mutually exclusive events because the occurrence of a head immediately nullifies, immediately prevents the occurrence of a tail. So therefore, coin tossing is an example of a mutually exclusive event. Now we move to the next understanding of the next term. You can see on the slide, this is exhaustive events. So exhaustive events means that if a coin is tossed, for example, or if a dice is rolled, one of these events must necessarily occur. So when you toss a coin, you either get a head or a tail. That means out of head or tail, one of them will obviously occur. Similarly, when you throw a dice, the number which you get at the top, either it is 1, or you get a 2, or you get a 3, or it's 4, or it's 5, or it's 6. One out of these possibilities, 1 to 6, has to occur. You cannot get a 7 because the die has 6 surfaces and you have 1 to 6 only. So when you throw the dice, the number which comes on the top must be out of either 1 or 2 or 3 or 4 or 5 or 6. That means one of these possible events must necessarily occur. This is meant by exhaustive. Finally, the third one. So probability has three basic, four, I will say, my understanding, four basic terms or concepts which you need to know. First is random experiment. Next, we discussed about event. What is event? Event is the outcome or the result of a random experiment. Third concept is mutually exclusive. Two events are mutually exclusive. Two or more number of events. If not more than one of them can occur simultaneously. Then what is exhaustive events? Exhaustive events means that out of the possible events, one of them must necessarily occur. So even when I'm talking about an examination, either I pass, I am declared successful, or I am declared unsuccessful. There is no in between. So either yes or no, either success or failure, right? So therefore, these are exhaustive events. And the last one is equally likely. That means equally probable events. That means when you throw a dice, all the there are six possible outcomes. That means 6 events, and each of them have equal chance. Of course, we are talking about a dice which is not tampered. Now, you may have heard about tampered dice, even if you think of epics like Mahabharata, you may remember. But we are talking about an untampered dice. There is no tampering, there is no manipulation in the dice. It's a simple untampered dice, and you throw it. So every number, like 1, at the top you can get 1 or 2 or 3 or 4 or 5 or 6. Each of them have equal chance or equal likelihood or equal probability of showing up. And how much is the probability? 1 by 6. So therefore, 2 events, head and tail, when a coin is tossed, is an example of a pair of equally likely events. And I hope now you are clear about these basic concepts. What is random experiment? What is meant by event? What is meant by mutually exclusive events? What is the meaning of exhaustive events? And finally, what do we indicate when we say that it's a mutually systematic events or equally probable events or equally likely events. So I'm sure you have understood this. And now we look at some simple formula from the ICAI study material, which we will use. We have to learn it by heart, and very simple, easy to remember formula, but we will use them directly when we go to the solution of the problems. So the first one we see here, two events A and B are mutually exclusive. That means P, the probability of A and B simultaneously occurring is 0. So you can see you have already learned about set theory. You know intersection of two sets. You are conversant with the union of two sets. So union we write as U, intersection we denote as an inverted U. So if two events A and B are mutually exclusive, that means what? It means that not more than one of them can occur simultaneously. So we can say that in case of a mutually exclusive event, the probability of A intersection B is 0. That means one of them, two or more of them, if you see, in case of mutually exclusive events, you can have two or more such events. But more than one of them cannot occur simultaneously. And as we saw, that occurrence of one event automatically implies the non-occurrence of the other events. So please remember that when we have two events A and B which are mutually exclusive, the formula to be applied is for P probability of A union B. This will be equal to what you see on formula 15.10. It is probability of event A plus probability of event B. Similarly, for three events A, B, and C, the probability of A union B union C is the sum of the individual probabilities of the events, PA plus PB plus probability of C, that is PC. The next formula, two events are exhaustive. Please recall what we learned by the term exhaustive. Exhaustive means that one of these events, out of a given set of events, one of them must necessarily occur. That means for finding out the probability of A union B, the total probability is 1. That means out of A and B, one has to occur with full certainty. So it could be either A or it could be B, but one out of them will occur. And therefore, it's an exhaustive event and it's denoted by a full certainty, so its probability is 1. Similarly, for three events, the same logic, we extend the same principle to three events A, B, and C. So probability of A union B union C is 1, where A, B, and C are three exhaustive events. That means one out of these three has to occur, necessarily occur. Finally, mathematically, so for each of these concepts, mutually exclusive, exhaustive, and equally likely, we are also learning the corresponding formula which we have to use for solving problems. Okay, so you can see here for the mutually exclusive events, both for two events and three events, we have the formula. Then we have proceeded to discuss about the formula for exhaustive events. And finally, if there are three events, A, B, and C, which are equally likely, then we can say that the probability of A has to be equal to probability of B, and this will be equal again to probability of event C. And this is shown in 15.14 on the slide. Right, I hope you're able to understand and slowly you are able to grasp the principles of probability. Now we move on to the next slide and we look at the classical definition of probability, and then we will see the modern, the current definition as we call it. So the well-known scientist and mathematician Bernoulli and Laplace, two of the most celebrated mathematicians, physicists, and statisticians, they had given the definition of probability, and the classical definition of probability is also known as a priori. So it is also known as a priori because of a reason, and the reason is because probability of the event A is defined on the basis of prior knowledge. So if you look at the a priori definition of probability, let us see what the study material explains. So it says, you consider a random experiment, means an experiment which has absolutely, equally likely results. You cannot predict which result will happen with certainty. So a random experiment that result in n finite elementary events, which are assumed to be equally likely. And then out of these n events, say you denote NA such that these are favorable to the event A. So then the probability comes to NA divided by N. That means the numerator is number of equally likely events which will be in your favor, which will be favorable to the event A, divided by the total number of equally likely events. So this is the basic definition, or the a priori, also referred to as the classical definition. Finally, we look at the modern, or you can call it the modified or the latest definition. So here, in fact, this particular definition we will use for solving the problems. Here, the idea is the numerator, we will have number of mutually exclusive, exhaustive, and equally likely events, which goes to the favor of event A. That means which are favorable to the event A, divided by total number of possible events, which are mutually exclusive, exhaustive, and equally likely. So this is what we have so far as the a priori definition is concerned and the modern definition is concerned. And now the last one, the last important principle we see before moving on to some problems is that what is a sample space? A sample space, you can call it, is a set, like a set, but it's non-empty. It has some members. Is a set which contains the elementary events of a random experiment. So please note, this is called a sample space. So what is a sample space? If I flip a coin, so it will be a set which will have only two outcomes or events. So either H or T, head or tail. So this is for a flipping of a coin. When I roll a dice, you can see there can be 6 events, and we denote it through the sample space denoted by S, capital S. This equals, then you open the set, use the set notation, and then you write the symbol of set, and then you write all the 6 events, possible events which can happen. These are equally likely, equally probable. Definitely these are exhaustive, and these are mutually exclusive. So this is what is meant by sample space. So we have discussed about the concept of what is a random experiment. Then we talked about what is event, then what is mutually exclusive. We learned about what is exhaustive events, and then we moved on to discuss the definition of what is equally probable, equiprobable events, equally likely events. And thereafter, we have looked into what is meant by sample space. So now looking at the probability part from the ratio perspective. So probability has a maximum value. Probability of any event would have a maximum value of 1 and a minimum value of 0. So when is probability equal to 0? When it is impossible event. And even if you know it's certain, sure, then we say that yes, probability is 1. Now, what is complementary event? So complementary event means, say if I say that I want to flip a coin, I toss a coin, and the event favorable for me, say, is a head. That means if I get a head on throwing the coin, I will get 100 rupees from my friend. So it's favorable for me. On the other hand, when I throw the coin, if a tail appears, then I have to pay 100 rupees to my friend. So it is unfavorable for me. Getting a head is advantageous. I will earn something. It is, we can call it favorable. on the other hand, if I get a tail, then it signifies that I have to pay 100 rupees to my friend. That means it is unfavorable for me. So what is meant by, now we look at what is complementary. So here I will say that occurrence of one event, A, we show it by the probability PA. So if event A has happened, that means when we toss a coin, there are two chances, two possibilities, two events, head or tail. So if I say what is the probability of a head which we are getting, it is PH, that is probability of getting a head, this is half, 1/2. So the complementary event of this is what? The probability of getting a tail, because it is the, when the head is falling, when the head is appearing, it signifies that a tail is not appearing. So it signifies the non-occurrence of a tail. So non-occurrence, that event which does not occur, its probability, that is called complementary event. And therefore, the probability of a favorable event and the complementary event is always equal to 1, because either of this will always happen. Finally, we will look at some of the ratios here through this small diagram. You can see when we say it is 0, we say impossible, probability 0. When typically we think of a probability 0.25, yes, we say unlikely. When it is when probability of an event is 0.5, we will say equally likely. When say for example, someone tells you that you have a 75% chance of passing the exam, so you say, yes, it is likely that I will be able to succeed in the CA Foundation exam because my probability is 0.75. And when you get the idea that, yes, someone has told you that you are getting the probability of passing the exam for you is 1, that means it's a sure shot. It's a certain event that you will pass the exam, you will be successful in the exam, and therefore the probability is denoted by 1. So you can see the different shades, the different values, some of the values which the probability of an event can assume. In this context, please remember that even when there is a credit sale, I'll just take you to accounts for a while. You might be knowing, you are aware about provision for doubtful debt, provision for bad debt. So this provision for bad debt, provision for doubtful debt, these you will later learn. I'm sure some of you might be knowing it, but others will definitely learn in due course. Even the provision for bad debt, the provision for doubtful debt is a matter of chance. It's a matter of estimation. It's a matter of probability. And you will later on see that probability principle, which we are discussing now in this chapter, this is used even for calculating the possible provision for a bad debt or the possible provision of a doubtful debt. So even in accounts, you can see a direct implication, a direct application of probability. Now we move quickly to the set of theories, the theorems we will learn, and then we will proceed to the problem solution. So we are on slide number 6, and now we see the theorems. For any two mutually exclusive events, that means the probability that either A or B occurs is always given by the sum of the individual probability. That means PA plus B is equal to PA plus B. P probability of A plus B, please see, 16.18. The probability of either A or B, that either A occurs or B occurs, is given by the sum of their individual probability. This is going to hold good only when A and B are mutually exclusive. And then we see one more, and that is for any two events, A and B. Let us see theorem 3 now. Theorem 2 is again a very simple, it's an extension of the basic concepts. Theorem 3 says for any two events A and B, the probability that either A or B occurs is given by the sum of the individual probabilities of A and B less the probability of the simultaneous occurrence of the events. So if it is mentioned or if you feel that these two events are not mutually exclusive, in that case, we will use formula as per theorem 3. So there what we will do, we will find the probability of either A or B occurring. We will use the formula probability of A plus probability of B minus probability of A intersection B. That means first we will see the chance of probability A, then we will add it with the probability of B, and from there we will deduct the probability of A intersection B. That means the probability that A and B occur simultaneously. That part we will deduct. So this will give you the formula. And when you know that two events A and B are mutually exclusive, then we use the simpler formula, which is given in 16.18. And this is, sorry, 15.18. You will see it is P probability of A plus B. This is equal to probability of A plus the probability of B. So it is a sum of the individual probabilities. So we'll remember these three important formula, and let us see the illustrations now, and we will have better understanding in the through the next few slides. It's just a process of understanding. Just keep your concentration, listen very carefully, and slowly we will be reaching a stage when we will start solving the problems. So here the first question from the ICAI illustration. Example 15.1, coin is tossed 3 times. What is the probability of getting 2 heads? There are 2 parts to the question. First one, what is the probability of getting 2 heads? And the next part says at least 2 heads. So when the coin is tossed 3 times, first, let us see the elementary events. What can be the individual ways of either the head will come or the tail will come? What can be the possible patterns? Let us see first. So now when you are tossing a coin 3 times, let us see what are the total possibilities. So please see, this is what we have done here is a sample space. We have drawn the sample space. Of course, I've just not drawn in the notation for the sample or the indication, but what you see here is typically a sample space. So it can be head in all the 3 throws. You are tossing the coin 3 times. In each of the toss, you might end up getting a head. So H, first possibility. The second, it could be HHT. That means first is head, then head again, and third is tail. The third possibility could be HTH. In this way, you can see all possible events. These are elementary events, and this is equal to 8. Possibility is 8. Now the question number 1, the first part of the question says, what is the probability of getting 2 heads? Now, out of these 8 outcomes which you see in the sample space, in how many cases do you get 2 heads? Let us see. From the sample space, you can see that 2 heads will occur in only 3 cases. Either you have HHT, or you have HTH, or you have THH. That means I'm getting a total number of 2 heads. I'm tossing the coin 3 times. I'm getting 2 heads. That means the combination is like this, 2 heads and 1 tail. Because there are 3 tosses. And we know that coin tossing is both mutually exclusive event as well as an exhaustive event. Therefore, either I'm getting head, and then tail, or it could be head, tail, head, or it could be tail first, followed by head and head. That means 3 possible outcomes, and there are 3 outcomes here, which is favorable to us, and there are 8 possible events or outcomes. So the probability of the first part of the question, what is the probability of getting 2 heads? The answer to this is 3 by 8. Because number of favorable events is 3, and the number of possible events is 8. Now we look at the next part. The question now says, what is the probability of getting at least 2 heads? Now, at least 2 heads means what? It means that either you get 2 heads and 1 tail, or you get all 3 heads. So when I'm saying that at least two heads, that means what? It's either two heads or it is two head. First situation is either it's at least two heads means either you get two heads, which means it is one tail, two heads and one tail. And the other possibility is that you get all three heads. Similarly, if I say that when I'm rolling a dice, what is the probability of getting at least four? At least four means a score which is equal to 4, or it could be more than 4. So it could be 4, 5, and 6. So if I say what is the possibility of getting a score which is at least 4, at least 4 means 4 and above. So here also we see that at least two heads means two heads, one tail combination, or it could be exact three heads. Now, out of the given sample space, out of the 8 elementary events or outcomes, how many cases are there where we are getting two heads and three heads? So if we see this particular case, you will find that two heads is occurring in how many cases? In 3 cases. And the probability of getting 3 heads, how many events are there? Only one event is there in the sample space where you get H, 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 and that is the first event. That means the probability of getting at least 2 means the probability of getting exactly 2 and the probability of getting more than 2. And in this case, it is 3. The probability of getting 2 heads is given by 3 events out of 8 events, and the probability of getting exactly 3 heads is given by 1 event out of 8. So total probability comes to 3 by 8 plus 1 by 8, that is 4 by 8, and that gives you 0.5, 50% chance. So this is the solution to the first illustration. Now we see a question on a card, a pack of cards. So this question is from the example 15.4. What is the chance of picking a spade or an ace, not of spade, from a pack of 52 cards? So usually, a card is having 52. A pack of cards has 52 cards, and there are 13 spades, 13 hearts, 13 clubs, and 13 diamonds. Each of these groups of 13 also has an ace. The question is, what is the chance of picking a spade or an ace which is not from spade? So that means here we find what is the chance of picking a spade? Well, the chance of picking a spade is 13, because we have 13 possible, 13 spades are there out of 52. And therefore, we can say the total number of elementary events is 52, no doubt, out of which picking a spade or an ace not of spade, the possible number of events will be 16. And therefore, the probability in this scenario is 16 by 52, which comes to 4 by 13. So this signifies the possibility or the probability of picking a spade or an ace not of spade. So picking a spade can be achieved in 13 ways out of possible 52 ways, and the ace not of a spade. So the ace can come either from the set of hearts or clubs or diamonds, and therefore there are 3 additional options or 3 additional events. So it gives us 16 by 52. Now we proceed to look at some further theorems, which we have already gone through in the past, in the last 2-3 slides. It's just a recap. 2 events are mutually exclusive. We saw if P A intersection B is 0, that means for 2 mutually exclusive events, P, probability of either A or B happening is the sum of the individual probability, as you can see, P A plus P B. For 3 events, same thing we discussed. If 3 events are equally likely, please remember this slide is given as a recap. If 3 events are equally likely, then it means probability of A equals probability of B. It is equal to probability of C. And then we have similar theorems, and we will also see that in case, let us come to the important results here. If A and B are two independent events, that means one cannot influence the other event, then the probability of occurrence of both will be given by something called PAB, denoted as P probability of A intersection B. These are independent events. That means occurrence of one event cannot influence the occurrence of another event. For example, today it is going to rain or not. So it is either it will rain or it will not rain. So this is event A. It has two possibilities. It will lead to, say, raining or not raining. So we can think of a situation on whether it will rain or not. So there are two possible events. Now there is, say, another experiment, random experiment, passing the exam. I will either pass or fail. Either I am successful or not. So two independent situations, passing the exam and raining, they cannot influence each other. So they are independent events. But in case we find that if there are events which are dependent on each other, then we have to use conditional probability, which we'll see in a few moments from now. In this slide, we will see what is meant by conditional probability, where the probability of occurrence of two events. Here we see the probability of occurrence of two events simultaneously. It's called a compound probability or a joint probability. And here we see that if the occurrence of one event B is influenced by the occurrence of event A, then these two events are known as dependent. In the last example on the preceding slide, we were dealing with a case where two events are absolutely independent. So the probability of two events occurring together was given by PA into PB, probability of event A into the probability of event B. But here we see a situation which is known as conditional probability, and this is denoted by a scenario where the occurrence of one event B is influenced due to the occurrence of another event A. So here we use another term which we see, P probability of B slash A, which is how will you read it? We will read it as probability of the event B given that event A has already occurred. For example, unless I'm able to qualify in the CA foundation exam, I cannot register for my CA intermediate course. So these are two incidents. So passing CA foundation exam is a prerequisite for getting registered in CA intermediate course. That means we can say that the possibility of registering in CA intermediate course is influenced, please note, is influenced. It has a bearing, it depends on whether I first pass CA foundation. So here we will say event B, that is the possibility or the probability of registration of CA intermediate course, is dependent on the probability of passing CA foundation. I hope you are able to understand what is meant by dependent events. In this case, the probability of A into B, that is both of them occurring, product or a compound probability, occurrence of both the events. So this will be denoted by probability A into probability B slash A. So this is called the conditional probability. As you can see, it is given by probability AB is equal to probability A multiplied by probability B slash A. Alternatively, we can write probability AB as probability B first multiplied by probability A by B. So we see the two theorems or the two formula which we see, which is there on this slide, and this deals with conditional probability. Okay, so now we will look at some of the other examples. So you can see probability of A intersection B, theorem 5. AB is also known as product of A, B is denoted by A intersection B. So this is denoted by probability of A into probability of B by A. Conversely, it can be written as probability of B into the probability of A slash B. For three events, similarly, we can use the formula which is given in theorem 6, same. Let us see the example. Rupesh, please see this solved example 15.15. Rupesh is known to hit a target in 5 out of 9 shots, whereas David is known to hit the target in 6 out of 11 shots. What is the probability that the target would be hit once they both try? Very interesting question. So first we are looking at these solved examples, then we proceed to the exercises. So here Rupesh is known to hit a target in 5 out of 9 shots. So the probability that Rupesh hits the target is, we can say, 5 out of 9, 5 by 9. David can hit the same target in 6 out of 11 shots. So the probability of David hitting the same target is 6 by 11. The question says, what is the probability that the target would be hit once they both try? So now they are both trying. So we can say that if both of them are trying, both are trying, the question is the probability that the target would be hit. Now here you can see probability of A, that is Rupesh hitting the target, is 5 by 9, and the probability of event B, that is David hitting the target, is denoted by 6 divided by 11, 6 by 11. Now here, probability of A intersection B, that means the probability of hitting the target jointly, it is given as what? The question is saying, what is the probability that the target would be hit once they both try? So both are trying. Both are trying. And here we see that A and B, in the given situation, we can see if as A and B are independent events, so P A intersection B is given by the product of the individual probability. We have 5 by 9 into 6 by 11, which is shown as 10 by 33, because A and B are independent. The target can be hit by any of them, both of them. So Rupesh hitting the target, this does not influence David hitting the target. So Rupesh can hit individually with a probability of 5 by 9, and David can hit the same target with a probability of 6 by 11. They are absolutely independent. The fact that Rupesh is hitting the target cannot influence David in any way. These are two disjoint events. So therefore, the probability, they are not dependent. So we are using the formula PAB equal to PA into PB. So it's given by 10 by 33. Finally, the question is the probability that the target is hit. So this is shown by PA union B, or it can be written as PA plus B. And you know the formula, it is given by PA plus probability of B minus the probability of AB. So individually, we have 5 by 9 plus 6 by 11 minus the joint probability, that is the compound probability we are reducing. We are subtracting that. So we have 5 by 9 plus 6 by 11 minus 10 by 33. You get 79 by 99. So this gives us the question of how we deal with problems where we have independent events and where we can get dependent events. Now we look at random variable and the probability distribution. So this is towards the end, and then we will start with the examples. We will solve at least 20-25 problems. So we look at random variable. This is from 15.9 portion 15.9 of the chapter on probability, or chapter 9 from the study material. So there are variables. We have discussed this earlier, if you recall, when we started with statistics, chapter 13, statistical description of data. We had talked about, explained what is discrete variable and continuous variable. So in case of a discrete variable, So here, first we are taking the example of a coin tossing. So coin toss means it's a random variable. Whatever result will come is a random variable. Because we cannot say with certainty that it will be a head or it will be a tail. So in the case of a random, what is meant by a random variable? A very good example is when we are tossing a coin. The sample space shows the number of head or tail. So this is an example of a random variable. And such a random variable can be of two types. Either it's a discrete variable or it can be a continuous variable. That means discrete random variable or it can be a continuous random variable. Number of heads in a toss of coin. Can it occupy, number of heads can always be, see, number of heads. So you are tossing a coin, say, 5 times. What is the number of head you can get? Either you get 1 head. Of course, you can get 0 heads, all 5 are tails. You can get 1 head or 2 heads or 3 heads or 4 or 5 or 6. Oh, sorry, 5 times you are tossing, 5 heads. So 0 to 5. That means the number of heads can only occupy or only assume specific values. Here it is only going to assume values from 0 to 5. It cannot assume a fraction. It cannot be negative. Similarly, the number of car accidents can only be positive integer. Of course, it can be 0. No accidents in a particular day. But it cannot assume negative value. You cannot have -3 accidents. Similarly, you cannot have a fractional number of car accidents. I cannot say that, okay, today the number of car accidents, car crashes is 50 whole 3 by 4. I cannot do that. It has to be a whole number. So number of car accidents, number of heads, these are all examples of discrete. Discrete means what? It is specific values. On the other hand, continuous random variable, please recall our earlier discussion when we started with chapter 13. So it could be height or weight. Of course, weight cannot be negative, but weight can be a fraction. Height cannot be negative, but height can assume any value, including positive values. It could be integer, it could be a fraction. So these are examples of continuous random variable within a defined range. The profit of a company can be fractional. It can be 0 as well. So we can say even the profit, the financial results of a company's operations could be seen as a continuous random variable. Based on this, we will see later that there are 2 types of probability distribution. Please just remember these distribution for the time being, because in the next chapter we will carry on from where we are leaving now. Probability distribution will be of 2 types. These are discrete and continuous. Discrete probability distribution means that there are 2 types. One is called the binomial distribution. The other is known as the Poisson. It is written as Poisson, pronounced as Poisson. Continuous probability distribution means the continuous random variable can take all values in a defined range. So it is not possible to assign probability to individual values. Whereas in case of a discrete random variable, it is possible to prescribe or assign probability to because in case of discrete random variable, it is taking specific values. So it is possible to identify which values it is going to occupy and to assign respective individual probability. But in case of continuous probability distribution, the random variable can assume all values in a given range, so it is not possible to assign individual probability. There we will use a curve or a graph, and that is known as the probability density function. We will take this up in chapter 16. Please note chapter 15 on probability is the foundation of chapter 16. So I hope you are following chapter 15 discussion carefully. We have started with each of the concepts we are discussing in a phased manner. We are going slow to make you understand learn gradually, but based on this, the next chapter, probability distribution, will be absolutely based on the foundation we are creating today. And then there we will see that there are two types of probability distribution, also known as theoretical distribution. Binomial and Poisson is for those distributions which are in the nature of discrete, where there is a discrete random variable involved. In case of a continuous random variable, it gives us a continuous probability distribution. It will be denoted through a curve, and a classic example of continuous probability distribution is the normal distribution. So this much, please try to follow, understand, and remember. Lastly, we look at the expected value, and then we start with a series of problems. Expected value of a random variable is simply the product of the value and the probability it can assume. So the mathematical expectation is given by sigma pi xi, where pi is the probability that it gets a value of xi. So if I put it in this way, say, the probability of, say, passing a particular exam, say, is 1 by 3. The probability of passing a particular exam is 1 by 3. 1/3 chance that I will pass the exam. Now, if I pass the exam, say I will get a prize, a cash award of, say, 6,000 rupees. If I pass the exam, I will get an award of 6,000 rupees. So here, what is my mathematical expectation? Well, my mathematical expectation is equal to EX, and that is equal to the probability of passing the exam into the monetary amount. So I will say my mathematical expectation is 1/3 into 6,000, because if I pass, I will get an award of 6,000 rupees. So 1/3 into 6,000, that means my mathematical expectation is rupees 2,000. That is called expectation. And for expectation, of course, we have variance as well. Here again, please see that we are making use of mean, arithmetic mean, which we learned earlier. You may remember that mu is the way we denote mean is through mu. Positive square root of variance, again, the standard deviation we are using here. And same thing which we discussed in the last session on dispersion, that if y equal to a plus bx for two random variables, and say x and y are related in this way, y equal to a plus bx, expected value of y will be given as what? It will be given as mu y equal to a plus b into mu x. And the standard deviation of y again will be given by modulus b, very similar to what we saw, change of origin and change of scale. So even in the case of standard deviation, we know that standard deviation, mean deviation, range, these are affected only due to a change of scale. These are not affected in case of a change of origin. Here again, we see that the standard deviation of y, therefore sigma y, is given by sigma x into modulus of b. That means the absolute value of b. And mathematical expectation, as we saw, it is sigma pi into xi. That means the probability and the corresponding value. We will now look at some examples, and then we will see that you will be able to completely understand and get clarity through the practical examples. So a lot of theorems are there, so that's why please go through them, understand. In some cases, you have to quickly memorize and then start applying. Once you start applying the different formula in a number of problems, slowly and slowly, you will get the grip on this particular chapter. So let us see the example of expectation. The question says, this is from the ICAI study material. It says that a business person is making a profit of 50,000, or he can get a loss of 20,000. Fine. And it further says that the probability of making profit or incurring loss is given by 0.75 and 0.25. The question is, what is his expected profit? What is his expected profit? Now, he can either get a profit of 50,000 or incur a loss of 20,000. The corresponding probability of profit is 0.75 and the corresponding probability of incurring a loss is given by 0.25. Please see the values given in the question. That means the expected, what is his mathematical expectation? His expectation is sigma pi xi. So here we will say that his expected profit is given by pi, sigma pi xi. That means 0.75 is the probability of earning a profit. If he earns a profit or if he makes a profit, he will get straight away 50,000. So we are multiplying the probability of profit by the amount of profit. Probability multiplied by amount. This gives you the expectation. So we have 0.75 into 50,000 plus 0.25 into minus 20,000. Why minus? Because it's a loss. So the complete expression which you see here is probability of profit into the amount of profit plus the probability of a loss into multiplied by the amount of loss. So therefore, the composite expectation is rupees 32,500. Expectation, mathematical expectation will have the units. It is not unit free. So it will have a unit. In this case, it is rupees. Now we look at another example where you see the application of permutation combination, more precisely combination. So we have a packet of 10 electronic components and it's known to include 2 defectives. That means 10 components are there, out of which 2 are defective. That means 8 are good items and 2 are defective. You are drawing a sample of 4 components at random. What is the probability that a sample does not contain more than 1 defective? Does not contain more than 1 defective. That means it is maximum it can be 1 defective, not more than that. So here, not more than 1 defective. This can have 2 events which will favor this statement is either there is no defective or you have exactly 1 defective. The question says not more than 1. That means either I have 0 defectives or I have at most 1, but not more than 1. I cannot have 2 defectives and more. In the question, it is given, once again, please see at most. That means not more than 1, at most 1. So it is either 0 or 1. Now the probability of getting 0 defectives and the probability of getting 1 defective, this we can easily calculate if you use the idea of combination, permutation combination chapter. That means I can draw what are the possible outcomes. The total number of electronic components is 10. So I can select any 4 of them in how many ways? 10C4. So that is in the denominator. Out of the 10 components, 8 of them are defect free. They are good items. So the probability of not getting a defect means that the probability is I am getting a good item. How many good items are there? There are 8 good items. Total number of items is 10. So in how many ways can I select 4 items which are good? 8C4, because there are total 8 items which are good and I have to select 4 out of them. So in the numerator, you can see 8C4 divided by 10C4. This gives you the probability of 0 defective. That is no defective. And probability of 1 defective means you are ultimately selecting 4 items. Probability of exactly 1 defective means that out of the 4 items, 1 is defective. That means in the box, we have 2 defectives. Out of that, you are drawing 1, which is defective. So it is 2C1 multiplied by 8C3, because out of the remaining 8 defectives, you are selecting 3. Sorry, out of the 8 good items, you are selecting 3. In the second part, you can see 2C1 into 8C3. This signifies the probability of exactly 1 defective. I am drawing 4 items. Out of that, exactly 1 is defective. That means the other 3 are good items. Total number of good items is 8. And out of the 8 items, I will select 3. So it can be done in 8C3 ways. and the remaining item is 1, because out of 4 items, 3 are good, 1 is defective. That defective item I can select in 2C1 ways. You can see 2C1. So together we get the probability. So this is an application. This chapter has a lot of applications from permutation combination as well as from dispersion, and even your background knowledge of the principles of central tendency also is put to use. We see another classic example. Random variable has the following probability distribution. Value is given and the corresponding probability is given. We need to find out, is given that find out ultimately the variance here. So we first find out Ex, expectation of X, and that is worked out 0 into 1 by 3. That means probability into corresponding value. So we work it out, we get 1. And then we calculate the expectation of X square. So in X square, you can see we are squaring each of the values given and multiplying it with the probability. From there, the simple formula of variance, we are getting the answer comes to 1. So this is yet another important example. And now we proceed to the last one. A very interesting question here. A speaks truth in 60% cases and B speaks the truth in 75% cases. In what percentage of cases they will contradict each other in stating the same fact? Very interesting question, and this is based absolutely on your logical reasoning and common sense. The calculation is pretty simple, but first is to understand what the problem intends to know from you. The probability of A speaking the truth is 60%. That means the probability of A speaking the truth we can write as 60 by 100. That means, okay, 60 by 100, we'll leave it to that. Probability of B speaking the truth is 75%. That means 75 by 100. The question is, in how many cases, in what percentage of cases they will contradict each other? That means if A speaks the truth, B will lie. B will not speak the truth. Only then they will contradict. And when B speaks the truth, A will speak the lie. Please try to understand. Only in this scenario, they will contradict each other. So the probability of A speaking the truth is 60 by 100. And the probability that A speaks the truth and B speaks lie. B speaks the truth, probability 75 by 100. So B lying, B not speaking the truth is what? It's the complementary event. So probability of B is 75 by 100. What is the complementary event? The event that B does not speak the truth. That means B is uttering a lie. That is how much? 1 minus 75 by 100, that is 25 by 100. So the joint probability that A speaks the truth and B is lying, this is given by 60 by 100 into 25 by 100. You get 3 by 20, first part. And then the next scenario is B now speaks the truth, but A is speaking a lie. A is lying. So this is possible when we calculate in this way. The probability of B speaking the truth is 75 by 100, and the probability that A is lying is given by how much? Is given by 40 by 100, because the probability of A speaking the truth is 60 by 100. So probability that A is speaking the truth is 60 by 100. So the probability that A is not speaking the truth, that means A is lying, is given by the complementary event. This is what I was explaining earlier. Complementary event. It is given by how much? 1 minus 60 by 100, that is 40 by 100. In this way, we are getting the second scenario. Once you add up both of them, you are getting 9 by 20. It's a fraction. The question says, in how many cases? In what percentage of cases? So 9 by 20 into 100, that gives you 45%. So this is again a very interesting question. With that, we move to important questions, and we will take a number of, we will deal with number of questions here. First one, let us take is the probability that a man will be alive in 25 years is 3 by 5, and the probability that his wife will be alive is 2 by 3. The question says, what is the probability that both will be alive? And second question, at least one of the two will be alive. Please note, probability of the man being alive, let us call it PM, as you can see, is given by 3 by 5. The probability that the wife is alive in 25 years given by 2 by 3. Let me also tell you from here, probability has a tremendous impact and application in insurance. Mortality table. You know, there is a subject called actuary. There are professionals who are known as actuaries, actuarial science. If you just do an online quick search, you will find the entire world of insurance and actuarial valuation depends on probability. Mortality tables. How does an insurance company find out the amount of premium? How do they arrive at the value? Because they will look at the probability that a person aged 20 years or 30 years or 55 years or 60 years will live till the age of 80 or 90. So another example, another practical application of statistics, probability specifically, you will find in the insurance sector. Right. So from this, I just thought of drawing your kind attention. So here we see the probability of the man living another 25 years is 3 by 5, and the probability of the woman is 2 by 3. The wife is 2 by 3. So the complementary event, that means the man will not live more than 25 years. This is given by 1 minus 3 by 5, complementary event. And the complementary event that the wife will not live, that means the wife will die in the next 25 years, is given by 1 minus 2/3. So now we get the question, we answer the first part. What is the probability that both will be alive? Both will be alive means these are independent events. So simply it's a product of two individual probability. Probability of the man living 25 years is 3 by 5. Probability of the wife living 25 years is 2 by 3. Just product of these two probabilities. Why? Because mathematically speaking, once again I say mathematically speaking, the probability that the wife is alive for the next 25 years is not dependent on whether the husband is alive for the next 25 years. These are independent from the mathematical point of view. So we multiply the individual probability and we get 2 by 5. So that is the answer to the first question. Both will be alive. Next is at least one of the two will be alive. One of the two, at least one of the two will be alive. So this is given by the union. Probability of M union W, that means that is equal to probability of M plus probability of W minus probability of M intersection W. That means here 3 by 5 plus 2 by 3 minus 6 by 15. And that gives you 13 by 15. Now the next problem, we will take up very important problems from the chapter of probability. We take the second one. A person is known to hit a target in 5 out of 8 shots. Another person can hit in 3 out of 5 shots. Find the probability that the target is hit when they both try. So event A here we write as first person hits the target, and event B is another person hits the target. So PA, first person is given by 5 by 8, and event B, PB is given by 3 by 5. Now, the question is find the probability that the target is hit at all when they both try. So here we see event X, target is hit when they both try. So when they both try to hit the target will be hit when at least one of them is able to hit the target. This is possible by, you can see the explanation given here, when at least one of them hit the target. So this is given by, now one of them hit the target means what? The complementary event, the opposite is that the target is not hit at all. The target is not getting hit. So in this way, if you just put in the probability, it's a direct application of probability, and here the question is basically the complementary event we are finding out. Probability of at least one hit means what? Probability of one hitting, both hitting. What is the complementary event of hitting the target? Complementary event means the target is missed, it is not hit. Both are failing. So applying this principle, we get Px, that is at least one of them are hitting the target, we get it as 17 by 20. Because we have seen that if both are hitting the target, we have got the probability. And then we have worked out when at least one of them are hitting the target, what is the probability? Next one we see is a pair of dice is rolled. If the sum of the two dice is 9, find the probability that one of the dice shows 3. This is an example of conditional probability. And here we see the pair of dice, a pair of dice is rolled. 2 dice are rolled. A pair means 2. If the sum of the 2 dice is 9, so the 2 numbers which appear on the upper part, on the top, any numbers can come. When you throw a dice or when you roll a dice, any number from 1 to 6 can come. It is seen that the sum of the 2 numbers which appear once you throw or once you roll 2 dice, it is 9. The sum is 9. Question is, find the probability that one of the dice shows 3. So this is an example of conditional probability. So here we are using the formula PAB equal to PA, probability of A, into probability of B by A. Probability of B by A means the probability of event B, assuming that event A has already occurred. So this is where we are using the conditional probability. Now, when the 2 dices are thrown, you can achieve how many events can be there. The first dice can, the number which comes on the top, any number out of the 6 can come. Similarly, for the second dice, any number out of the 6 can come. So total possibility is 6 into 6, 36. Total possible outcomes. Probability of A. Now, the sum is 9. 9 you can achieve only when you have 6 and 3. First dice gives you 6, second dice gives you 3. The second combination can be 5, 4. Third combination is 4, 5, and the fourth combination is 3 and 6. That means 4 specific favorable events out of possible 36 events. So that gives you 4 by 36. And then we have the probability A intersection B. That means here the question is one of the dice, find the probability that one of the dice is 3. Now, if one of the dice is 3, the other has to be 6. This is shown by the probability A intersection B. That means here we have only 2 options. The first event was getting a total of 9. This can be done in 4 ways. 6, 3, 3, 6, 5, 4, 4, 5. But the question now says, yes, you have got 9, but one of the dice is 3. That means the other has to be 6. So the combinations are 3, 6 and 6, 3. 2 outcomes out of 36 possible outcomes. So therefore, the probability which is required, find the probability that one of the dice shows 3. So you can see here we are finding the conditional probability. And here we have already got the probability of A intersection B, which is 2 by 36. So we divide that by probability A, and that gives you the probability of B, assuming A has occurred. It's a conditional probability of B. And in this way, we arrive at the given answer, half. So some of these problems, once again, please go through, understand the steps which are clearly visible on the slide, my explanation. And I'm sure these are some of the tougher ones we have taken deliberately because it is important to know the tougher ones. If you are able to handle tougher problems, then definitely easier problems for you will be, you will have a higher probability of solving easier problems. Now let us look at the exercise. We are on slide number 14 and we are starting with the exercises now. And here we'll take some questions from set A. Probability of getting ahead when 2 unbiased coins. So we are starting with set A, and the question reads, probability of getting ahead when two unbiased coins are tossed simultaneously. Probability of getting a head. Two unbiased coins are tossed. So probability of getting a head, so it can be either HT. How many possibilities are there? It can be HT, TH. It can be head and tail, tail head, head and tail tail. 4 possibilities. Now, question is of getting a head. A head means either one head or it could be two heads. Now, if we see the probability of getting one head, of getting a head, they are saying. So probability of getting one head is, okay, now they're saying only probability of getting one head, sorry. Not if they ask probability of getting at least one head, then we will consider one head and two heads. But here the question is probability of getting one head, a head. That means exactly one head. This we can get through two possibilities, HT and TH. So therefore, two favorable outcomes, two favorable events for us, and possible number of events is 4. So you can see the probability works out to 2 by 4, that is half. Because probability formula you know is the number of favorable events divided by the number of possible events. But these events all need to be mutually exclusive, exhaustive, and equally likely. We take the next question, 49th question, and we see here a bag contains 15 1 rupee coins, 25 2 rupee coins. Okay. So we are starting with, we are commencing our understanding of the next question. 15 1 rupee coins, 25 2 rupee coins, 10 5 rupee coins. If a coin is selected from the bag, probability of not selecting a 1 rupee coin. Probability of not selecting a 1 rupee coin means what? This probability is the complementary event of selecting a 1 rupee coin. So if you see, we have, how many coins are there in all? We have 15, 25 and 10. Total number of coins is 15 plus 25 plus 10. That is 50 coins. If you select a coin at random, that means you can select it in 50 ways. So possible number of events is 50. In how many ways can you select a 1 rupee coin? We'll first find that. In how many ways can you select a 1 rupee coin? The bag has 15 1 rupee coins. So if I want to select a 1 rupee coin, there are 15 ways. 15 chances, 15 out of 50. But now the question is asking, if a coin is selected, find the probability of not selecting. Not selecting means we need to find the complementary event. The probability of selecting a 1 rupee coin is 15 by 50. So the complementary event is what? The probability of not selecting a 1 rupee coin, that is given by 1 minus probability of the given event. Here the given event is 15 by 50. That means we are first assuming the probability of getting a 1 rupee coin. So we just find out the complementary event, and therefore we subtract the probability of this event from 1. 1 minus 15 by 50 gives you the probability of the complementary event. That means the probability of not selecting a 1 rupee coin. This is 49th question. Next, we have another very interesting question. A, B, C are 3 mutually independent events. They have a probability 0.3, 0.2, 0.4. What is the probability of P, A intersection B intersection C? So we know when events are independent, what is the probability? What is the joint probability? It is just the product of their individual probability. So here we have, the question gives you the individual probability of A, B, and C. Just multiply. So 0.3 into 0.2 into 0.4, that gives you the joint probability that A, B, and C are occurring together simultaneously. That means all of them are occurring. 51st question, if 2 letters are taken at a random from home, what is the probability that none of the letters would be vowels? Well, none of the letters would be vowels. So this is the word home. So we have 4 letters here. And if you see out of home, there are 2 vowels and 2 consonants. Question is, if 2 letters are taken at random from the word home, what is the probability that none of the letters would be vowels? None of the letters would be vowels means they would be consonants. How many consonants are there? There are 2 consonants. That is H and M. The vowels are O and E. Now you can choose 2 consonants. You have two consonants. You have to select 2 from there because the question says 2 letters are selected at random. This can be done in 2C2 ways. Selecting 2 numbers from or 2 letters from 2 consonants is 2C2. So the favorable number of events is 2C2 and the total possible number of events is 4C2 because you can select 2 letters from a group of 4 in 4C2 ways, and that gives you the probability 1/3. Okay, next question is based on the earlier trend which we were discussing, that if y equal to ax plus b or a plus bx, then what is the expectation? We were discussing about mean deviation, standard deviation. So question says, if x and y are random variables having expected values of 4.5 and 2.5 respectively, then the expected value of x minus y is how much? Well, this is a simple application. We know that if we have ex is given, expectation of x is given, and the expectation of y is given, if we have to find out the expectation of x plus y, very simple. It will be the addition of individual expectation, ex plus ey. Similarly, if ex is given and ey is given, like you see in this problem, and if the question says find ex minus y, very simple, it is just ex minus ey. We subtract the expectation of y from the expectation of x. So here ex is 4.5 and ey is 2.5. So ex minus y is simply equal to 4.5 minus 2.5, which is 2. Okay. Next question, number 54. Variance of a random variable is 23. And what is the variance of 2x plus 10? Continuing with the same trend, variance of a random variable is 23. Okay. What is the variance of 2x plus 10? Now, if you say y equal to 2x plus 10, now here we have the variance. Now, variance of y will be equal to, variance we know is the square of the standard deviation. So the formula for variance of y is equal to b square into the variance of x. So therefore, what we see here, the variance of x is how much? Is 23, and the value of b here is 2, because it is given y equal to 2x plus 10. So you can see the value of b is 2 here. So the formula is variance of y is b square into variance of x. Variance of x is 23 and b square is 2 square, which is 4. So the answer comes to 92. 55th question, what is the probability of having at least 1/6 from 3 throws of a perfect die? A perfect die is thrown 3 times. What is the probability of having at least 1/6? So therefore, the question is again an application of complementary event. Probability of having at least 1/6 means 1 minus probability of having no 6. At least 1/6 means what? You can get 6 and the other 2 may not be 6. It can be 2 6s and the third may not be 6. And it can be all 3 6s. At least 1/6 means this. So what is the complementary event of at least 1/6? The complementary event is no 6 will come. So therefore, probability that no 6 will appear, this is given by 5/6, because you can throw the dice, you can roll the dice in 6 ways. And if you want to get a number other than 6, that means the favorable outcomes will be what? It can be 1, it can be 2, it can be 3, it can be 4, it can be 5. 5 options. So when you roll the dice once, the probability of not getting a 6 is given by 5/6. We are throwing 3 dice. And these are independent events. So 5 by 6 into 5 by 6 into 5 by 6. Therefore, we now find out the complementary event. And the probability of the complementary event is what? 1 minus the probability of the given event. The given event is probability that 6 will not come. The complementary event is what? The complementary event is probability that at least 1 6 will come. So I hope you can understand 1 minus 5 by 6 cube. And then you can work it out. Set B, we are taking questions. If two unbiased dice are rolled together, what is the probability of getting no difference of points? Another very interesting question. So we are currently on slide number 15 and taking up the questions from set B. If two unbiased dice are rolled together, unbiased dice you are rolling together, what is the probability of getting no difference of points? That means the number which shows on the top will be same for both the dice. That is why there is no difference. If you throw two dice, if you roll two dice and say on one dice you get 4 and on the other dice you get 6. So the difference is 6 minus 4, 2. But no difference is only possible when you are getting the possible favorable outcomes is either both show you 1 or both show you 2 or both show you 3 or 4 or 5 or 6. That means the same number comes on the top. That's why there is no difference. So this is only 6 ways in which you can do it. Either it's 1 1 or 2 2 or 3 3 or 4 4 or 5 5 or 6 6. No difference will come in these 6 cases. So favorable events is 6. Total number of possible events is 36 because you can roll the dice, 2 dice in 6 into 6, 36 possible ways. And out of that, 6 ways are favorable to us. So the probability is 6 by 36, which gives you 1 by 6. So I hope you are able to see the logic and the reasoning. And this chapter, as you can understand, is towards the end of the last 2-3 chapters are left. So probability is interesting, but yes, you have to be very cautious and understand, conceptually clear. Then only you will be able to rightly answer the question. But you can see the advantage here is once the concept is clear, there is no complicated formula, right? You don't have to create tables. It's just a mathematical fraction. You are dealing with few fractions. Question 12, for two independent events A and B, what is PA plus B? Given that PA is 3/5 and PB is 2/3. Now it is given that A and B are independent events. Now we know that if A and B are independent events, PAB, that is A intersection B, is just the product of PA and PB. So first what we have done, we know you are supposed to find out PA plus B. PA plus B means probability of A union B. This is given by PA, probability of A, plus probability of B minus probability of A intersection B. That is AB. So the formula you can see PA plus PB minus PAB. PA is given 3 by 5. We have written 3 by 5. PB is given 2 by 3 and PAB is equal to how much? Is equal to 3 by 5 into 2 by 3. That is 2 by 5. It's just a product of the individual probability. So we get the answer 13 by 15. Question number 8, if ABC are 3 mutually exclusive and exhaustive events such that PA is 2PB equal to 3PC, what is PB? So it is given they are 3 mutually exclusive and exhaustive events. So we can just reason in this way. Probability of A equal to twice the probability of B equal to 3 times the probability of C. Let us equate them to K. So we can write that 2 into PB, because PA is 2 into PB. So 2 into PB plus PB plus 2/3 of PB is 1 because they are exhaustive. So from here you can see PB, probability of B, comes to 3 by 11. So here you see these are 3 exclusive, mutually exclusive events, and the relation is given. We equate them to K. and then just put in the value, because A, B, C are mutually exclusive, exhaustive. That means the total sum, probability of A plus probability of B plus probability of C, has to be equal to 1. They are exhaustive. Exhaustive means one out of them has to occur, and together it will be equal to 1. So just substituting the value of each of the probabilities, we arrive at the PB value, which is 3 by 11. So what we have done here is we have converted PA in terms of PB. That's why instead of PA, we have written 2PB. And instead of PC, PC is equal to what? 2PB equal to 3PC. So we can say PC is 2 by 3, 2/3 of probability of B. So that is why we have written 2/3 of probability of B. Okay, so I hope you are able to follow. Some of them are little critical, just pay more attention and you will understand. Next question, what for if for two independent events A and B, A union B is 2/3 and probability of A is 2 by 5, what is probability of B? It is given two independent events A and B. So we have to find out probability of B. We know the formula P A union B equal to PA plus PB minus PA intersection B. We also write P intersection B as PAB. And since A and B are independent events, PAB is equal to the product of the individual probability, PA into PB. So first we find out PAB. PAB is equal to the individual product of PA and PB. But here we don't know how much is PB. But we know PA union B is 2/3. So what we do is we can write PA plus PB minus PAB is 2/3. PA we know is 2 by 5 and PB we are yet to find out, but PAB we can find out because PB multiplied by PA, which is 2 by 5, that gives you PAB. So solving, we get the value of PB. So here basically PA is how much? PA is 2 by 5 plus PB, which we don't know, plus we have PAB. PAB is basically 2 by 5 into PB. Because PAB is what? A and B are independent. So the joint probability of A and B is simply equal to the product of the individual probabilities, PA into PB. Accordingly, we can solve it and get the required answer. 19th question, it is given that a family of 2 children has a girl. What is the probability that the other child is also a girl? So I have selected deliberately the difficult ones so that you are getting, because many students might get stuck in these questions. These are the relatively difficult ones. Easier ones I have not touched here. We will see number 19th question in this way. It is given that a family of 2 children has a girl. What is the probability that the other child is also a girl? 2 children has a girl. Now, in a family of 2 children, what are the possibilities? Either you have boy, girl, girl, boy, both are boys or both are girls. So this defines the sample space. BG, GB, BB, and GG. Right? I'm sure you will agree. Next, if you see, the question says, first we are finding out probability of A, one child is a girl. Because the question says, it is given that in a family of 2 children, there is a girl. What is the probability that the other child is also a girl? So here, please note very carefully, first we are finding out probability of A, that one child is a girl. One child is a girl, we can get 3 favorable events because one child is a girl, 3 out of 4 possibilities. So it is 3 by 4. One child is a girl, we will take BG option, GB option, and also GG, because one child is a girl, even there's one possibility. Even in case where both the child are girl, this will hold good. So 3 out of 4 possibilities. Now that is 3 by 4. Now PAB is what? PAB is the probability that the other child is also a girl. The probability that the other child is also a girl, please be very careful here. Please listen very, very cautiously and with full concentration. PAB means both are girl. Both are girl. What is the probability? Out of the sample space, BG, GB, BB, GG, only GG option will be the right answer. That means only one event. That means probability of AB, both are girls, is given by 1 by 4. And therefore, the probability of conditional probability, that is probability of B/A, B by A, this is given by PAB. It's a lovely question, beautiful question. But yes, a little you have to think and then you arrive at the right answer. So here PAB means the probability that both are girls. And we are trying to find out the conditional probability if one is a girl. So question is, if one of the child is a girl, what is the probability that the other child is also a girl? So here we are finding first PAB, signifying both are girls, that is 1 by 4. And then we are finding the probability of PA, that is one child is a girl, that comes to 3 by 4. And therefore the conditional probability, that means if one child is a girl, the other child is also a girl. It is conditional. This is given by, you know, the value or the formula PAB equal to PA into PB by A. This is for conditional, where the events are dependent on each other. So this comes to 1 by 3. 19th question is definitely not an easy one. I would certainly agree on that. 21st question, if a random variable X assumes 0, 1, 2 with probability, what is the expected value? And well, the expected value is very simple. Just multiply the corresponding value with the probability, because expectation of X is sigma P into X, where P is the probability and the X is the corresponding values. 23rd question is also fairly simple. We have done similar problems. The variance of X is given 6. Variance of Y we have to find out. So Y we are writing as minus 4 by 3 plus 2x by 3. That means here the value of B is 2/3. We know the formula variance of Y is equal to B square into the variance of X. Please remember, in the earlier discussions for standard deviation, mean deviation, range, the formula was that the standard deviation of Y or the mean deviation of Y is equal to B into the standard deviation of X, or B into the mean deviation of X. But here for variance it is B square. So therefore B square means 2/3 square, that is 4 by 9 into the variance of X. Variance of X is 6. So we have 4 by 9 into 6, that gives you 3 2s are 6, so 8 by 3, yes. 20th question. Okay, we will see this question here for two independent events. What is PA plus B? So if PA is given and PB is given, it's fairly easy. This is an easy one. PA plus PB minus PAB. So that is 3 by 5 plus 2 by 3 minus the product. PAB, these are independent. So PAB is equal to PA into PB. So we will get the value. Coming to set C, if an unbiased coin is tossed 3 times, what is the probability of getting more than one head? Probability of getting more than one head. So total cases, unbiased coin is tossed 3 times. So how many possible cases? It is 2 cube. 2 into 2 into 2. 2 to the 4 to the 8. 8 possible cases. The sample space I have shown here, either you get 3 heads, or you get head, head and tail, or it could be head, tail and head, or it may be tail, head and head. What is the probability of getting more than one head? So for more than one head, this is the sample. So out of 8 possibilities, the favorable events, we are having 4. So the probability comes to 4 by 8. 10th question, a problem in probability was given to 3 CA students, A, B and C, whose chances of solving. So individual chance of solving, the question is given. What is the probability that the problem is solved? That means The problem is solved. That means here we want to find out. That means here any of them is able to solve. That means here P A union B union C. So this formula you might be knowing, P A union B union C is equal to P A plus PB plus PC minus PAB minus PAC minus PBC plus PABC. So you can easily see it from the Venn diagram. And therefore, what you see here is the answer comes to 11 by 15 if you just apply the formula. 12th question, Tom speaks truth. This one we have done earlier, so the same process. Tom speaks the truth in 30%, Dick speaks the truth in 25%. What probability they will contradict? So that means situation will be 2. When Tom speaks the truth, Dick will speak the lie. And when Dick speaks the truth, Tom will speak the lie. So you find the probability of Tom speaking the truth and Dick speaking the lie. That means it will be the complementary event of Dick speaking the truth. So you just apply the same process. We were explaining the last example and you will get the right answer. Finally, we come to the last part, number of questions we have been looking at. This is the MTP on probability mock test paper, very important for your preparation. What is the probability that 4-digit number comprising 2, 5, 6, and 7 will be divisible by 4? 4-digit numbers. The digits are given 2, 5, 6, and 7. Now, what is the probability that the number which you create out of 2, 5, 6, and 7 will be divisible by 4? All of you will remember the rule of divisibility by 4. What does the rule say? Say there are 4 numbers. Say a number with 4 digits. If the last 2 digits are divisible by 4, then the entire number will be divisible by 4. In this question, it asks you what is the probability that 4-digit number comprising from 2, 5, 6, 7 is divisible by 4. First, we find out total number of possible outcomes. Now, how can I select 4 digits out of 4 numbers? 4 out of 4. So we are using permutation here, 4P4. We get 24 cases. Now, how many will be favorable to us? This is where the intelligence you have to apply. Those numbers which ends with 5 and 6, that means it can be 2756, it can be 7256. 2 last digits are 5 and 6. 56 is divisible by 4. Therefore, if the number is 2756 or 7256, it will also be divisible by 4. So we have first looked at the possible cases as per the rule of divisibility by 4. 5, 6, these 2 digits can occupy the last 2 positions in 2 factorial ways. Similarly, another possibility 7, 6. So if the last 2 digits are 76, automatically 76 is divisible by 4. So this can be done in 2 factorial ways. Similarly, 52 and 72. Therefore, if you see the total number of favorable cases comes to 2 factorial into 2 factorial into 2 factorial into 2 4 times. And 2 factorial is how much? 2 into 1, that is 2. 4 times means 8. So the probability comes to 8 by 24. Right? So this is also very intelligent question which came in the MTP. Now, second question, what is the probability that 4 children randomly selected have different birthday? Looks like very tricky, but just let us apply the basic logic. 4 children have different birthday. So now let us select one child, first child. Say his birthday is 1st of March. So out of 365 days, his birthday can fall on any day. So I can write 365 by 365. The second child will have a different birthday. That means now out of 365 days, the favorable days will be 364. Because the first child's birthday has to be deselected. Every child will have a different birthday. So say the first child's birthday is 1st March. Out of 365, 1 day is gone. So now the second child's birthday can fall on any day excepting 1st March. I hope you understand the logic. So therefore, that means the second child, well, the probability will be 364 by 365. In this way, the third child, out of possible 365 days, his favorable days will be 363 because 2 days are already gone. Because 2 days means the first day is the birthday of the first child, the second day is the birthday of the second child. So in this way, for 4 children, the answer will be 365 by 365 multiplied by 364 by 365. Then you multiply it by 363 by 365. And for the fourth child, the probability is 362 by 365. It's a huge number, approximately boils down to 98.36. Third question in connection with the random experiment. So each question we are understanding, breaking it down into parts, applying the reasoning, also connecting with the relevant formula, and then arriving at the solution. In connection with the random experiment, it is given that PA is given 2/3, PB is 3 by 5, PA union B is given. You need to find PA dash B, that A slash B, that means the conditional probability. The answers are given, the options are given. So first we find out from the PA union B equation, we need to find PAB. PAB is very simple to find out. You know that PA union B is PA plus PB minus PAB. So you can easily get PAB equal to 13 by 30. And they are asking you PA in PA slash B, that means conditional probability. PAB means probability of AB is how much? This is equal to PB into probability of A slash B. So from PAB, if you divide it by the probability of PB, you will get the correct answer. So this is the conditional probability direct formula which is used. The fourth question of MTP, in a non-leap year has 366 days. In a non-leap year, the probability of getting 53 Sundays or 53 Tuesdays or 53 Thursdays is what? In a non-leap year, the probability of getting 53. Now, normally we say 52 weeks because 52 into 7 gives you 364 days. Okay, 364. In a non-leap year, that means this year is having 365 days. 52 weeks are over. So now we have the last day. 364 days are gone. So the 365th day, the last day of the year, the question is either Sunday or Tuesday or Thursday. Now the last day of the year can have 7 options. It can be a Saturday, it can be a Sunday, and so on. So out of 7 options, the question says, what is the probability that it is a Sunday or a Tuesday or a Thursday? That means 53 Sundays means what? It means that after 52 weeks are over, the last week starts with a Sunday. Similarly, 53 Tuesdays mean that 52 weeks are over. 364 days are over. The last week starts. And it starts with the 365th day, and this will be a Tuesday. That means the last day, 365th day, can occur in 7 ways, out of which only 3 will be advantageous or 3 will be 3. I think that means we can say these are favorable events. Out of 3, out of 7, only 3. It can be either Sunday or Tuesday or Thursday. Please note. So therefore, possible number of outcomes is 7 and possible number of favorable outcomes is 3. So the probability comes to 3 by 7. That means we are clicking option C. And this is the logic. I hope you are able to understand the explanation. Fifth question, if A and B are 2 events, PA is given, PB is given, PA union B is given. So this is, I think we have to find out the formula of PA slash B slash. So that is simply the conditional, the complementary probability of 1 minus, that is PAB, PA union B. So this also you can work out using the given values. We are looking at the RTP questions now. What is the chance of throwing at least seven in a single cast with two dices? So we have taken up number of questions for the explanation from set A, set B, and I guess we have also done questions from the MTP. Now we are taking the RTP so that you have a complete understanding of the type of questions which are there in this chapter. So what is the chance of throwing at least seven in a single cast with two dice? Now, at least seven. So at least seven in a single cast with two dices. Now, two dices. You are throwing two dice. How many ways can you, how many outcomes are there? Two dices are thrown, each having six possibility. So 6 into 6, that is 36. So we have possible number of outcomes, if you see, is 36. Now they're asking at least 7. At least 7 means it can be 7, 8, up to 12, because when you throw two dice, the maximum which can come, at least 7 in a single cast with two dices. So if you see in a single cast with two dices, at least 7. 7 you can get when you have 4, 3. It can be 2, 5 and 5, 2. It can be 1, 6 and 6, 1. So if you look at the possibilities for getting a total of 7, it can be 2, 5, or it can be 5, 2, or it can be 4, 3, or even it can be 3, 4. At least 7 they are saying. At least 7 in a single cast. So here 7, 8, 9, 10, 11, 12. So all possibilities we will have to check. And then you will be arriving at the probability 7 by 12. So possible number of outcomes is definitely 36, and then chance of throwing at least 7. So please note, this is at least 7 means it will be 7 and above. Now we look at the second question. An investment consultant predicts that the odds against the price of a certain stock going up is 2:1. So let us see this interesting question on investment. Odds against the price of a certain stock going up is 2:1. And the odds, that means the odds against the price of a certain stock going up is 2:1. That means we can see here that 2:1 means 2 by 3. That means the price of a certain stock will not go up. That is given by 2 by 3. That means the price of the stock will not go up. It is given by 2 by 3, because it says odds against the price of a certain stock going up is 2:1. And the odds in favor of the price remaining the same is 1:3. That means the probability that the price of the stock will remain the same, constant, is given by 1:3. That means 1 by 4. 1 divided by 1 plus 3. So that means here we see that the probability that the price will not increase is 2/3. Because 2:1 means 2 divided by 2 plus 1. And the probability that the price will remain same is given by 1 by 4. So what is the probability that the price of the stock will go down? The probability that the price of the stock will not go up, this is only satisfied under two conditions. If the probability, if the stocks remains same, if the price remains same, and if the price comes down. So two possible outcomes, favorable outcomes. Either the price of the stock remains same or the price of the stock declines. These two outcomes will be favorable for the event, because we want to know what is the probability that the price of the, it's given that the probability that the price of the stock will not go up is 2/3. It will not go up is 2/3. It will not go up means it will not go up only when the price is same or the price is declining. So 2/3 probability has two parts. has two scenarios. Scenario 1, that the probability that the price remains same. This is given by the probability 1 by 4. We have to find what is the probability that the price of the stock will go down. So this is the remaining option. So therefore, the sum is 2/3. From there, we deduct the probability of the price remaining same. So therefore, 2/3 minus 1 by 4 gives you 5 by 12. This is the probability that the price of the stock will go down. The third question, PA is given, PB is given, PA intersection B is given. Therefore, what is PA/B? That means the conditional probability they are asking. So here we know that PA/B is given by PAB divided by PB. So PAB is 0.25. I will divide it by PB. Probability of B is 0.36. So they want to know the conditional probability. So the answer is 0.25 by 0.36. You can just work it out and check. Fourth question, from the following probability distribution, these are from the RTP. So very important for your preparation. From the following probability distribution, we need to find expectation of X, EX. So you can see the value of X is given, the FX is given, that is the probability is given. We have to find the probability, we have to find the expectation of X. This is given by sigma xi into pi. That means here what we will do, the first value of X is 1 and the probability is half. So we multiply them, 1 into half. So we get half. Then we have the next value is 2 and the probability is 1 by 3. So we multiply them. It becomes 2 into 1 by 3, that is 2/3. And the last value is 3 and the corresponding probability is 1 by 6. We again multiply them. 3 by 6 we are getting, that is half. So if I add all these three, because expectation EX is the expectation of X, this is equal to the sum of the product of probability and the corresponding value. X1 into P1 plus X2 into P2 plus X3 into P3. In this way it goes on. So if I add up, I'm getting half plus 2/3 plus half, that is 1 whole 2 by 3. That means I'm getting 5 by 3, that is 1.67. Question 4, I hope this is clear. It's just a simple case of mathematical expectation which you need to calculate. We now come to the last part, and that is we take the RTP question, September 2026. So almost we are spending almost 40 minutes on the question, so that as many questions as possible we are trying to examine, understand, explain, and solve. Please see fifth question from the RTP series. Suppose E and F are two events of a random experiment. If the probability of occurrence of E is 1/5 and the probability of occurrence of F is given, of F given E, that means this is a conditional probability, then the probability of non-occurrence of at least one of the events E and F is what? So here we have to find out the probability of non-occurrence of at least one of the events. That means the probability of non-occurrence of at least E or F. This is given by the, please note, this is given by the complementary event that E and F both will occur. The complementary event that P and F will both occur means what? Complementary event of both occurring is the non-occurrence of at least one. So this is, if you see here, P probability of E and F both occurring. This is, we will just find the probability of this joint probability by using the individual given. PE is 1 by 5, it is given, and the conditional probability is given 1 by 10. That means PE into PE by F by E. So therefore we multiply that, we are getting 1 by 50. This means both of them are occurring, but we need to find the complementary event. So therefore 1 minus 1 by 50 gives you 49 by 50. This is the probability which is required in this case. The next question from the RTP September 2026 series is, what is the probability of getting neither total of 7 nor 11 when a pair of dice is tossed? You are throwing tossing a pair of dice, what is the probability of getting neither a total of 7 nor 11? So what we will do, we will first find out the number of cases when we will get 7 and 11. And then we will find out the complementary event. 7 and 11, complementary event is neither 7 nor 11. I hope you understand the concept of complementary event. So what is the probability of getting a total of 7 or a total of 11 when you toss or when you flip or when you roll a pair of dice? Each dice can have 6 ways of showing up. So total probability when you roll a pair of dice is 36, 6 into 6, 36. Total number of outcomes, possible outcomes. From here, we will find out the number of outcomes which is favorable to 7 and 11. Now, 7 I can get when we have 4, 3, 3, 4. We can also get 7 if we have 6, 1, 1, 6. And we can also get a total of 7 if you have 5, 2, and 2, 5. In this way, we will find out the total number of favorable cases in order to get 7. 4, 3, 3, 4, 6, 1, 1, 6, 2, 5, and 5, 2. So 1, 2, 3, 4, 5, 6 cases we are getting. Now, in how many cases can you get a score of 11? The sum will be 11. So this can be either we have 5, 6, or it can be 6, 5. So if you see, we are getting a scenario where to get a total of 7 or 8, 7 or 11, the total number of favorable cases we are working out 4, 3, 3, 4, 6, 1, 1, 6, 5, 2, 2, 5, and then we have 5, 6, and 6, 5. I am counting it on my fingers. It comes to 8 favorable cases. So this means 8 out of 36 is the probability of getting 7 or 11. 8 out of 36, if I just simplify, I am getting 4 2s are 8, 4 9s are 36, 2 by 9. Therefore, the complementary event, neither 7 nor 11, just the complement. So complement of an event is 1 minus the probability of the event. So 1 minus 2 by 9, we are getting 7 by 9. This is also very important, interesting. And I hope once you start solving these type of questions, I guess it will sharpen your processing power. Your brain also becomes sharper. And this helps you later when we take up the next chapter on theoretical distribution. 7th question from the RTP 2026 September, the latest current one, most important for our preparation here. What is the probability that a leap year selected at random contains either 53 Sundays or 53 Mondays? Now here you can see, I've just shown the reasoning. It is a leap year, please note. So please be very careful to read the question for every chapter. But probability, is, I think, more concentration, more focus is required because every word can have a different calculation, a consequence. Here it is given that it is a leap year. Leap year means, leap year comes once every 4. And on a leap year, we have 366 days. So I can break 366 into 2, 364 plus 2 days. 364 means 52 weeks are over. 52 into 7 is 364. It's a wonderful question, I must say. Thanks once again to the ICAI for giving us these type of questions in the MTP and the RTP, which I guess challenges our intelligence and makes us sharper. This is just my understanding. I guess some of you at least will agree with me. So here we see this is also logical reasoning. Leap year, 366. We know 52 days, 52 weeks makes 1 year. 1 week we have 7 days. So 52 into 7, 364 days are over. That means 52 weeks are gone. And now another week starts. The question says that this 364 days are gone. We have 2 days, 365th and the 366th day. 2 days are there. And now the question is, either it's 53 Sundays or 53 Mondays. Now, this can happen only when if you see, this can happen. The 365th day can happen in 7 ways, because the 365th day can be Sunday, Monday, Tuesday, 7 days. And also the 366th day can also be created in 7 days. Out of this, we need a Sunday, or it can be a Monday. So therefore, the 364th day is over, 52nd week is 52 weeks are gone. 53rd week either can start like this, Sunday, Monday, or we need to get a Sunday or a Monday. So either it can be Sunday and Monday, or it could be the other way around. We need to get 53 Mondays. That means it can be even Monday, Tuesday. If you get Monday, Tuesday, we are getting 53 Mondays. Also, if you get Saturday, Sunday, you will get 53 Sundays. So from here, now, out of 7 possible days, Sunday or Monday, this will come in 2 ways, 2 by 7. So in this way, if you just find out, here we are using PA plus PB minus PAB formula, and we are arriving at the answer 3 by 7. This is also very interesting question. Question 8, if A and B are 2 events such that PA is 1 by 4 and PB is 1 by 3, and PA union B is given, what is the value of PB conditional A, that is PB slash A? So for this question number 8 from the RTP September 2026, we first find out PAB. PAB. So PAB is equal to how much? We know PA union B is equal to PA plus PB minus PAB. So PA union B, if I work it, is equal to PA plus PB minus PAB, right? PA union B we are given, it is 1 by 2. So I write on the left hand side 1 by 2 equal to PA. PA is 1 by 4, PB is 1 by 3, but we don't know PAB. So how much is PAB? Well, PAB is equal to, if you just find out, it comes to 1 by 12. So now you know PAB is 1 by 12. PAB is 1 by 12. We have to find PB by A. PAB is written as PA, probability of A, into probability of B by A. So probability of B by A is equal to how much? Probability of AB divided by probability of A. So probability of AB is 1 by 12 and the probability of A is 1 by 4. So if you divide this, you are getting the probability of B by A. That means, how do we read this? We read it as probability of B, probability of event B, assuming that event A has occurred. That is conditional. So this is possible when we divide PAB by PA. And therefore, we get the answer 1 by 12 divided by 1 by 4. That comes to 1 by 3. Question number 9 to 11, the last lot, September 2026 RTP. Question number 9, if 2 dice are thrown, then what is the probability that the sum of the faces of the dice are square or cube numbers? It is again a beautiful question. Please see the question here, that the sum of the faces of the dice will be square or cube. Now, when you throw, the question is, if you're throwing 2 dice, the total sum will be either a square number or a cube number. How is it possible? So if you throw it, square number means we can say 4. If you get a sum of 4, 4 is 2 square, it's a square number. 5 is neither square nor cube. 6 also neither square nor cube. Next number is 8. 8 is a cube number. 8 is 2 cube. Also, the number 9 is again 3 square. So you are getting a squared number. If you get a sum of 10, well, doesn't serve a purpose. 10 is neither a square number nor a cube number. I can also get a score of 11. I'm throwing 2 dice. If I get 6, 5 and or 5, 6, I'll get a total of 11. 11 also meaningless for us. It is neither a square number nor a cube number. And even if you get the highest of 12, well, it also does not satisfy our condition. Our condition is that the sum which you get should be either a square or a cube. So we can get this lovely question, extremely beautiful and intelligent question. So the square number can be 4 and 9, and only one cube number is available, that is 8. So now we break it down into elementary events. From composite to elementary events, 4 we can get when you have 2, 2. Both the dice show you 2. 9 I can get if I get a 5 and 4, or it can be 4 and 5. Please see the combinations. 8 I can get if I have 6, 2, 2, 6. 4 I can also get if I have 1, 3, 3, 1. 8 I can get if I have 5, 3 and 3, 5. 9 I can get if I have 6, 3 and 3, 6. Also I can get 8 if we have 4, 4. I was just writing down the possibilities. So here, if I count the number of favorable events, I'm getting 1, 2, 3, 4, 5, 6, and it's 12 events I get. There are 12 favorable events such that these numbers, you can see these numbers. The sum of these numbers either will be a square number or a cube number. It will be a perfect cube or a perfect square. So out of possible 36 outcomes or events or results, only 12 are favorable to us. That means using the definition of probability, it is 12 by 36 equal to 1 by 3. The second question, we are taking number 10 now. Ram is known to hit a target in 2 out of 3 shots. So Ram's hitting possibility or probability is 2/3, and Sham is known to hit the same target in 5 out of 11 shots. So for the RTP, I'm taking all the questions, each of the questions, not a single question I'm leaving out. Same for MTP. So you can see for Sham, the probability is 5 by 11, and for Ram it is 2 by 3. What is the probability that the target would be hit if they both try? The target would be hit if they both try. Target would be hit. What is the complementary event that the target is missed? The target is not hit. The target is not hit when both Ram and Sham will miss. Please try to see the logical reasoning and the application of complementary event. The question is, what is the probability that the target would be hit if they both try? I am doing it in a different way. I am first finding out what is the probability that the target is missed. No one gets it correct. No one is able to strike. No one is able to hit the target. So when it's given that Ram has a probability of hitting the target, his probability is 2/3. That means probability that Ram hits the target is 2 by 3. So what is the probability that Ram misses the target? It's a complementary. So 1 minus 2 by 3. So probability of Ram missing the target is 1 by 3, because it is 1 minus 2 by 3. Please note carefully. If possible, later on you pause the video, listen to it in half speed, whatever convenient speed, pause it and then analyze, work it out step by step. These are critical questions, not easy at all. I mean, not on the face of the question. I cannot just apply a formula and get the answer. It requires reasoning. So the probability of Ram missing the target is 1 by 3, and the probability of Sham hitting the target is 5 by 11. So Sham also misses the target. That means probability that Sham misses the target is 1 minus 5 by 11, that is 6 by 11. That means now we have got the complementary event. Probability that Ram misses the target is coming to 1 by 3, and the probability that Sham misses the target is given by 6 by 11. So therefore, the joint probability that both miss the target is given by the product, because they are independent events. And this is how much? That is equal to 1 by 3 into 6 by 11. 1 by 3 into 6 by 11, that brings me to 2 by 11 if you multiply. That means the probability that the target is not hit, that means both of them, both Ram and Shyam, they are unable to hit. That probability is 2 by 11. So the complementary event of this is what? That means the target is hit. It could be hit by either of them. So 1 minus 2 by 11 gives you 9 by 11, which is the required probability in this particular case. We have the 11th question from the RTP 2026 September. A card is drawn from each of two well-shuffled pack of cards. The probability that at least one of them is an ace is what? So here we see each of the question in the MTP, RTP, and also in the exercises, so intelligent questions. And you have to, of course, conceptually, once you are clear, you are absolutely crystal clear about the formula, the logical reasoning, when to apply the formula for independent events, when to apply dependent cases, conditional probability. Rest of it is only practice. So if you look at the last question on the slide, a card is drawn from each of two well-shuffled packs. The probability that at least one of them is an ace. So the probability that at least one of them is an ace. A card is drawn from a pack of well-shuffled, two well-shuffled packs of cards. So the probability that at least one of them is an ace. Now, the probability that at least one of them is an ace means that at least one is an ace. Also, it can be both are aces. So what I can do is maybe here the possible outcomes or the favorable outcomes will be like this. At least one of them is an ace. So this can be picked in how many ways? So it can be picked in 4 out of 52. We will assume there are 4 aces. So 4 by 52. So both are aces. The probability is 4 by 52 into 4 by 52. One of them is an ace. That is 4 by 52. But the other is not an ace. This is given by 48 by 52. Please see the next probability. So I am drawing 2 cards. One card is drawn from each of the 2. There are 2 packs. I am drawing 1 card each. That means effectively I am pulling 2 cards. So the possible scenarios will be this. The left one, say on my left hand, this is an ace, this is not an ace. Situation 1. Situation 2. Left hand not an ace, right hand is an ace. And the last probability, both are aces. So let's take the last probability first. Both are aces. This is possible only when the probability of pulling an ace is 4 by 52. So first situation, we are assuming both are aces. 4 by 52 into 4 by 52. First scenario. Second scenario is that one of them is an ace and we are assuming that the left hand is an ace, right hand is not an ace. Left hand is an ace, probability is 4 by 52. Right hand not an ace, probability is 48 by 52. So the product comes to 44 by 52 into 48 by 52. Please see the next possibility. And similarly, the last possibility is left hand, I am pulling a card, it is not an ace. The right hand, I am pulling a card, this is an ace. So this situation is depicted by left hand, not an ace, probability is 48 by 52, and right hand, I am pulling an ace, this is 4 by 52. So therefore you see the last scenario is 48 by 52 into 4 by 52. If you just complete the calculation, it will work out to 25 by 169, which gives us the required probability. This is definitely interesting, and it's like a challenge, mathematical challenge, but it helps you prepare better for the exam. So with this, it's almost 4:45. With this, we will come to the recap. So please.
Very good evening, sir. Once again, very much
Good evening,
thankful
sir.
to you.
Please. Yes, sir.
Very well explained today's last. Interesting. Even though I prepared those RTPs and the MTPs.
Yeah, sir. That's why.
Quite interestingly, you have delivered very well.
Thank
Though
you,
I am prepared, that is, I can't able to sometimes maybe explain.
Sir, it's a pleasure. And okay, all students, so please, we have sir with us, and sir has prepared these questions for the RTP. Just see, I didn't know that sir had done it. Sorry for my ignorance, but you see, I was continuously marveling at the beauty and the intelligence which was hidden in the question. And it's a fortune for us that sir has rejoined, and you can see how these questions are prepared. So sir must have put in so much of thoughts and to test the intelligence and how you're applying.
Sir, before you completing,
Yes,
I
sir.
want to conclude some kind of basic things actually.
Yes, sir.
Sir has taken a very good number of examples, and whatever the more or less these kind of models are very, very, very important, which has been explained by the CA Arjit Chakraborty sir also. And once again, I would be very much thankful to CA Arjit Chakraborty sir on behalf of Board of Studies Academic. And over to you, sir. Further, you wish to say anything?
Thank you, sir. Thank you so much, sir. Thank you. Thank you, sir. So good to see that, we have good. I hope that students who are focusing and concentrating on each of these explanation and the formula. Yeah, I'm sure you are finding it interesting along with challenging. It's interesting. And I'm sure once you solve a problem on your own, you get a type of happiness and pleasure in your mind, which probably is very difficult to describe in words. And this feel good factor, if you do it for all papers, all subjects, all topics, well, then I will say you have a probability of passing the exam, and the probability will be 1. That is what I will say. So for a recap, please once again study be clear about what is experiment, random experiment, events, then absolutely the 3 parameters: mutually exclusive, exhaustive, equally likely events, which we had discussed earlier. Then the definition of probability and the different applications. Please be very clear about the formula: PA plus B equal to PA plus PB minus PAB. Also, please be very clear and understand sample space. I was sharing different practical examples of how to write the sample space. And last but not the least, conditional probability. We have done number of problems on the conditional probability, and you can see that PAB equal to probability of A into probability of B, assuming A has occurred, that is B by A. Conversely, we can write it as probability of B into probability of A by B. So please revise and revisit once again conditional probability. Mathematical expectation, we have done number of problems. It is nothing but sigma pi xi. And at the end, we were discussing also about the relation between 2 variables y equal to a plus bx. And if you are given the expectation of x, we have to find the expectation of y. And dear students, please do recall that the expectation of y, or rather I will say the variance, if you see the variance is given, you have to find the variance of y. So there we will have to use that same formula, b square into the corresponding value of x. Lastly, probability distribution. We were discussing about the random variable. These are of 2 types. Please be clear about the concept of discrete random variable and continuous random variable. And also, as we said, that the examples of discrete random variable, when you talk about the probability distribution regarding discrete random variable, we have 2 internationally acclaimed examples, and that is the binomial distribution and the Poisson distribution. And for the continuous probability distribution, we have something called the probability density function, and the example of this is normal distribution. These 3 distributions, which we have discussed in brief and outlined for you, will be the entire foundation on which chapter 16 on probability distribution is built upon. So that is what I request you once again to review from the session today and also from the study material. At the end, we have taken a number of solved examples from the ICAI study material. I was explaining them, and exercises from the solutions set A, set B, and the MTP, RTP. And as you could see that for September 2026 and the other RTP questions, each and every question has been so interesting and at the same time so engaging that I was trying to take each of them, understand, make you understand in steps and arrive at the answer, at the solution. So please do that. And it's good to know once again that Ravi sir has taken so much of efforts to create these questions. Creating a numerical question is indeed a challenging task. so we could do many of the questions. On that note, I will say once again, thank you for your time and patience, your efforts, and till we meet, work hard and practice continuously. Go on practicing as many problems from the exercises, the mock test paper, the RTP. Even if you have done a problem earlier, do it once again. Because once you do it, your speed, your accuracy, and your memory, everything works together. Work in such a way so that you can say with pride that, yes, the probability of passing the exam will be 1. So you pass with surety. So on this note, I thank Sir once again for his continuous presence, his encouragement to all the students and to all students for being part of the session today. I request the tech support team, sir, to kindly conclude the presentation for today. Thank you and see you next day. Yes, sir, we can complete. Thank you. Thank you.